Oh, what is up, guys? Welcome to Keegan Garage. Here we got car here, motorcycles here. Let's go.
So the basic system for air conditioning in a car is refrigerant moves through and into the evaporator and then goes into a compressor. And then on the other side, it's condensed and then an expansion valve.
The basics. Here on this half of the air conditioning unit, we have high pressure refrigerant coming down to the expansion valve, which, because this is from a high pressure area, then moving to a low pressure area of the system, the water or refrigerant immediately starts to boil, and breaking these bonds is an endothermic process. So as this refrigerant travels through the evaporator, air is forced right through the evaporator, and because this endothermic process is going on, the evaporator and the refrigerant inside of it absorbs all that heat that's coming through this incoming air, and ultimately leaving it freezing cold.
Okay, so after moving out of the evaporator and into the compressor, the low pressure gas on the left side is compressed and then moves into the condenser, which is a high pressure system, and then condenses, because it's high pressure, on the inside of the copper tubing, which, since that is an exothermic process, that heat must be removed. So on the condenser, near the condenser, there's a fan that removes that excess heat, and it continues into the expansion valve where the process repeats.
Now, just to reiterate, as our water here comes to a simmer, the heat from the air conditioning unit is not being destroyed, which one of Newton's laws that is. Rather, it's being moved. Remember how our evaporator is taking in the heat? Well, our condenser is rather just moving it outside of the car, not destroying the heat and cooling it down, if that makes sense. Now, we'll be back in a couple minutes while this boils.
This vaguely resembles what happens in the air conditioning of a car as refrigerant goes from high pressure to low pressure and evaporates within the copper tubing.
So much steam, guys.
Super steamy.
This sort of shows when refrigerant goes from low pressure to high pressure and condenses.
Okay, so if water can do the same thing as refrigerant, why don't we just use water?
Well,
the water is much harder to evaporate than this molecule known as 1112 tetrafluoroethane, otherwise known as refrigerant R134A, because water has hydrogen bonds which are much stronger than R134A's London dispersion forces and dipole-dipole, giving it a much lower boiling point as there's far less energy required to get there. And for this reason, it's much easier to manipulate for the purpose of refrigeration. When chemical refrigerants leak, they're put into the atmosphere. There, solar radiation breaks them down, releasing reactive atoms that aggressively destroy the protective ozone layer. This depletion allows dangerous ultraviolet radiation from the sun to penetrate directly to the Earth's surface. There, escaped gases also act as potent greenhouse agents, trapping heat and accelerating global warming.
So I am Dominic's dad. He asked me to discuss a few things about the internal combustion engine, one of my favorite things in the entire world. So in this garage, we have several different types and examples. My 2025 Corvette Z06. We'll show you this one. All right. This has a naturally aspirated 5.5 liter flat plane crank engine. And then over here, we have a few of my motorcycles. Down to another engine, right? So this is my 1962 Ford Thunderbird. You can see underneath here, there's another engine, right? I restored this one myself, and Dominic even had a hand in helping. Yep. All right, so this engine I have converted to fuel injection, right? Just for reliability purposes. So all the spark and fuel are now controlled by this little computer over here. So when I come to the car and I turn the key, so what you start with, right? Air will come through the air filter and it will go through the throttle body, right? So this little butterfly here opens and closes to let air in, okay? This is the intake manifold. Air comes into the intake manifold and then it gets mixed with fuel. So each cylinder, these little guys right here, those are fuel injectors. Fuel comes in to this rail up top, right? So actually the fuel line will connect right here to this rail, but the rails are the same on both sides because it's an 8-cylinder. You're gonna have 8 fuel injectors, 1 for each cylinder. So the fuel comes into the fuel rail system, right? It pressurizes this to 60 pounds per square inch, which is quite a bit. What'll happen, the computer on the car will pulse these little solenoids here, and it will allow the injectors to squirt fuel into the engine. The air will come in, right? And then it gets mixed with the fuel from the fuel injectors. So this would mount right here, this part right here would mount to the top of the engine, right? And this is where the valves are. This part would have the intake manifold sitting on it. So that fuel and air comes in here, right? It gets basically sucked in. The engine makes its own vacuum and the fuel and air gets sucked in here when the valve opens. There's another view of the valves, okay? And then the bad one, you have an intake valve and you have an exhaust valve. Intake valve is bigger and it's on the intake side, so it's easy to tell. And then the exhaust valve is on the exhaust side, right? Got your exhaust manifold. So what happens, that fuel and air comes in through the intake valve, right? When the piston is going down, it sucks in the fuel and air. When it comes back up, both valves close and that fuel and air gets squished, okay? Then what'll happen, the computer will fire, I don't know if you can see them on here, but spark plugs. So then the spark plug will fire and basically it'll make an explosion, right? Which will force that piston back down, and that's basically how the engine keeps running.
All right, brief overview of the combustion inside of the engine. So like Stuart said previously, we have our intake valve and we have our exhaust valve and our spark plugs in this sort of piston, container. So in our intake valve, we have our gas and our air, which comes into the intake manifold, and this comes to our fuel injectors. Then inside of the chamber, the piston will compress it, and then the spark plug will provide the activation energy for the combustion reaction, where it then explodes, pushing down the cylinder and creating, torque for the engine to run.
So, combustion, it's oxygen plus fuel goes to carbon dioxide and water. And then I'm gonna try and balance the equation with this generic hydrocarbon for gas.
Okay, so you're probably wondering, how does this produce so much energy to power cars? Well, let's take a look at our standard heat of formations of these compounds. So, come closer. Plug this into our thing here. Now, you don't need to be a very crazy mathematician to realize that this is very negative, okay? So, delta H equals negative. And this means it's a very exothermic process. This is going to be, the magnitude of this number is very high. So, when, we go through this, it's going to make a lot of energy. But we will next go into why do we need the spark plug to fire this reaction. Okay, spark plugs. Basically, in this reaction, if you look at a potential energy diagram, this is essentially what it looks like. Okay, potential energy of our reactants. But then this is where the kicker is. As we can see, very large delta H, okay? However, also large activation energy. So, our spark plug right here provides that activation energy for the reaction to occur, so then we can, ultimately release all that amazing stored energy for our cars. Road salts. Why does everyone hate road salt, right? I put a frowny face here because particularly here in the Northeast, we really hate road salt. So some of our typical road salts here are KCl, potassium chloride, sodium chloride, or magnesium chloride. And when these combine with water, they form an electrolyte solution. For example, KCl will form, will dissolve into K plus and a Cl minus. Now, in an electrolyte solution, the ions that are dissolved in the solution help facilitate the transfer of electrons. So let's, bring this back to our, rusting on our northeastern cars and why this salt makes it so much worse. So as we can see here, this is the reaction that occurs when, your iron in your car is rusted to iron oxide. So as we can see here, this is a redox reaction. Iron starts with an oxidation number of 0, and so does oxygen. But this quickly turns into +3, and this turns into -2. So as we can clearly see, there's a transfer electron somewhere, and because over here we have this electrolyte solution, the electrolytes actually help facilitate the transfer of electrons, which ultimately speeds up this, rusting process. Now, the other thing is that it doesn't stop when it's dry. You might think, oh, as soon as it's dry, as soon as your car is dry, right, it's gonna be fine. No. Salts are actually hygroscopic, which meaning they pull in water. So, the water will still rust your car, even when it's seemingly dry. It's, you're still gonna have to deal with problems like that. As we can see here in the Northeast, if we just look at some of our local Facebook Marketplace listings, our cars tend to take a lot of this damage. That salt, as we previously mentioned, really takes a toll. And oftentimes you may find that, people might clown on these, like this one, 1901 Ford something, like it's pretty funny. But yeah, the Northeast sucks for rusty cars. That's why a lot of people go with Southern cars. So as we can see here, we have the Thunderbird here, and right underneath here we have an undercoating. Now this is a protective measure against some of our, Northeast's most harsh salts. Even though we don't bring this out in the winter because it's too cool of a car to. these sort of measures, you know, kind of eat up the salt for the iron that's in the body, which ultimately, you know, expands its lifetime and yeah, prevents a lot of rust in the car.